three categories of electrolytes: strong, weak, and non. And to recognize what strong electrolyte is, we just look. Is it a soluble salt? We have to know the solubility rules. Is it a strong acid? There's 7 common strong acids. Didn't we finish all of these? 7 strong acids. What are they? Perchloric, chloric acid, hydrochloric, hydrobromic, hydroiodic acid. Which one? Nitric. And sulfuric. Yeah. So if it's one of these, it's a strong acid. If it's one of these, then we call it a strong electrolyte. And then we have the strong bases. And the strong bases are also strong electrolytes. And what a base is kind of the opposite of an acid or antithesis. In other words, if we have an acid solution, we can neutralize it with a base. One of the common bases is sodium hydroxide. So if we have an acid like hydrochloric acid and a base like sodium hydroxide, the base will neutralize the acid and form sodium chloride and water. So we get table salt and water. So this is the base. So if it's strong base, what are the strong bases? There are a number of them. A little bit more complicated than the strong acid. These are the soluble hydroxide. Soluble hydroxide. What are the soluble hydroxides? Well, most hydroxides are insoluble. So which ones are soluble? Well, if we go down, hydroxides are all insoluble except for group 1 and ammonium. Sodium hydroxide, sodium is a group 1, so this is a soluble hydroxide, also a strong base. Group 1, ammonium and calcium. Calcium. What else? Did you write them down in your notes from last time? We didn't get that far. We didn't do the solubility rules. Did anybody write down the solubility rules for hydroxide? You haven't? Strontium. Okay, calcium, strontium, and barium. Those 3. Well, those are the soluble hydroxides, and those are all strong bases. What else? There's others. The others would be soluble sulfides. What are the soluble sulfides? Group 1, ammonium, group 2. That's correct. And so those would be strong bases. Soluble sulfides, and then soluble oxides. Now, sulfur and oxygen are in the same family, so they're going to share similar properties. except oxide is a little smaller. You know, sulfide's S2 minus, oxide is O2 minus. So you might think they're probably comparable, but you know, if I asked you, what would your guess be for oxides? Would you have a guess? And that is, it depends. You know, some people would say, well, it's not a fair question because oxides weren't on the list. You know, species. Since oxides weren't on the list of species that I gave you for the solubility rules, then you might think it's unfair. It's an unfair question. But it's not really an unfair question. It's a fair question. It's a fair question. It depends on, you know, what your level is. You know, there are people who are people who are struggling just to memorize the solubility chart. And then there are people who have the solubility chart memorized. And then there are people who are beyond that. You know, there are people who are beyond. Well, how can you be beyond memorizing? The people who are beyond that are the people who have the leisure to maybe examine the solubility chart, the solubility rules, and think about them. You know, I was watching this documentary about Rome, and they said a lot of the technological achievements of Rome was because people weren't out looking for food all the time. You know, people weren't out gathering and hunting. You know, they had farming pretty well down. And so what that did was it freed up a lot of time. It freed up a lot of time so that they could think about these things in more detail. And they're talking, it's actually a documentary on the development of concrete. And the Romans developed concrete and concrete architecture that survives today. And so it's quite an achievement. But they were saying, you know, a large part of that, why didn't other cultures develop concrete, or why didn't this happen? And they were talking about, well, it's because the Romans had time to think about it. Well, that's the same thing with solubility rules. You know, the people who already have it down and who review it every day, when you review it every day, it gets tiring, and then you start looking for things, you know. You start looking for other things to make it interesting. And so you might see some patterns in the solubility rules. Is it just straight memorization, or is there some pattern to it? Turns out there is a pattern to it. You know, the most soluble species are, and this has to go back to Coulomb's law. Does anybody remember Coulomb's law? Okay, Bruce.
Well, from my physics class, it's like K times Q times, well, it's like Q over R is the distance between the two charges.
Okay. Yeah, in physics it would look like this. You know, force is equal to some constant times Q1 times Q2 divided by R squared. I just said in our class, I talked about this, I think, did I talk about this the first week of class, I think? This is the first week of class. So I just said forces are going to be just proportional. Force is proportional to, we use Z, the charge on ball A times the charge on ball B, or species A times the charge on species B divided by R, the distance between the center charges squared. And so how do we apply something like this? How we apply something like this is we look at, you know, what has strong forces. You know, things that have a strong force will be higher charge or lower charge, a bigger Z or a smaller Z. Higher charge. The higher the charge, the bigger the attraction or the bigger the repulsion. And the other factor it depends on is the distance between the center of the charges. You know, the distance between the center of the charges depends on the size. And so the higher the charge and the smaller the size, the stronger the force. So when we look at it, one thing that a group 1 ions all have in common is they're all +1. Ammonium, +1. And those are actually fairly big. And so another way of thinking about Coulomb's law is something called charge density. Charge density. If I have the same size, this one's +1, this is 2+. Which one's going to have a higher charge density? The 2+ is your charge, and therefore it's going to have stronger force. If I have this one, a plus on a big versus a plus on a small, which one has a higher charge density? The small one, this one. It's more concentrated. And so the more concentrated the charge, the higher the charge density. And so when we think about the mostly soluble, the all soluble would be like these are things that you notice after you go through it the 50th time, the 100th time. After you go through something 100 times, you start to see things that you don't see. Like I was watching this YouTube and they were talking about the film. Was it the it was just a short thing about the film. They were talking about how many times they watched it because they miss things. You know, they miss things. The first time they see it, they miss it. And the second time, the third time, and then they start to see all these little details. When I was at UCLA, I took history of French film. And history of French film, we had to watch each film twice. The first time and then the second time. And obviously the second time you start to see things you didn't see the first time around. Well, the same thing with the solubility rules. After the 100th and 50th time you look at it, you start to see things you didn't see before, right? And so that's what I mean by going beyond, because one of the things you might see that you didn't see before is that, you know, all the soluble species are low charge. Nitrates, acetates, chlorates, all -1. Group 1, ammonium, +1. All the insoluble species are of higher charge. What's the least soluble species on the solubility chart? Phosphates. Phosphates are what charge? -3. -3. Carbonates? -2. Chromates? -2. And so those types of things you notice. So the repetition, the reason I say, you know, go through your notes every day is two reasons to go through your notes every day. One reason is so that it's burned into your memory. That way you can recall it rapidly. Speed counts. The other reason I say to go through it every day is so that you can notice things that you don't notice before, and then you can make. And so something like this, oxide, well, you need a little bit more information. One bit of information that you probably don't know is that oxide is smaller than sulfide. Sulfide's bigger. And so I'd expect oxide to be less soluble. But it's hard to get a gauge. So it turns out like group 1 and ammonium are the soluble oxides. You know, other oxides like rust, you know, is rust iron 3 oxide very soluble? No, not at all. You can't wash rust off. It'd be great if you could, but you can't wash it off because it doesn't dissolve, it's not soluble. So that's a lot of questions are like that I notice on tests, you know, just one step of level, or one level harder than just memorizing stuff. Okay, so we have soluble oxides. We also have soluble, actually, let's not call it soluble. We have the amides. The amides most of them are soluble because amide is an anion you haven't seen before. It's an iodine, but it's not a monatomic elemental ion. It's NH2 with a minus charge. So that's amide. Most amides are soluble. What happens when you dissolve? an ionic compound. Take a look. What do we call this structure? Lattice. This would be an ionic lattice. So what we have is this. This is Coulomb's law in action. If you're, let's say this is a this is positive, this is potassium chloride. If this is potassium ions, that's positive. So if you're positive, then you want to surround yourself with as many negatives as possible. So you try to put, and in fact, you can put 6 of these negative ones directly in contact. These purple ones are slightly out. So we have 6. And if you're purple, you want to surround yourself with as many greens. So we have 6 of those. 1 out here. And this whole thing is held together by electrical attractions. You know, the attraction between positive and negative. So what happens if you take this crystal, this salt crystal, and try to dissolve it in water? Well, it doesn't stay as a crystal, right? What happens is the crystal gets torn apart or broken apart or dissociates. In other words, the ions all break apart and the lattice pretty much falls apart. Well, it depends on how strong this lattice is. If this lattice is very strong, then it doesn't want to break apart. It doesn't want to dissolve in water. If this is like sodium chloride, it dissolves. Sodium chloride would dissociate and break apart the lattice. But if this were something else like magnesium phosphate, then it's not. The lattice is too strong. The lattice is too strong. Water is not going to be able to break it apart. All right, so this is the soluble salts, the strong acids, and the strong bases. Now, the strong bases don't do this. You know, for the strong, we say these dissociate or ionize completely. Bases don't ionize. Bases do something else. Bases do not ionize / dissociate. Instead, they hydrolyze. Hydrolyze. Acids actually can do both. I'll talk about what I mean by hydrolyze in a little bit. Hydrolyze is just react with water. All right, so we have strong electrolytes, and we'll look at these. We'll look at examples of these as we go along. And then we have weak electrolytes. How do you recognize what a weak electrolyte is, or how do you determine? And so, if we're looking at weak electrolytes are some heavy metal salts. Some heavy metal salts have a different structure. You look at the periodic table. The heavy metal salts would be down here. You know, things like lead, thallium, mercury, gold. These are heavy metals, or heavy metals. Some of those, like lead is kind of weird because lead-2 chloride is an ionic lattice. However, lead-4 chloride is molecular. It's PbCl4 molecules, so you can call it lead tetrachloride because it is molecular. Okay, some heavy metal salts, we aren't really going to get into this. Weak acids are weak electrolytes. So what weak electrolytes do is they partially ionize, dissociate, hydrolyze. Partially do that. So weak acids. Well, what are the weak acids? These are the 7 common strong acids. And so what we're going to do is we're going to make an assumption. We're going to assume if an acid is not one of the strong common acids, it is weak. There are some strong acids that aren't very common. So hopefully you don't run into those less common strong acids, and then this will work. And then we have weak bases. Initially, for the weak bases, initially we'll just look at a chart. Salt chart. But later on, we'll try to figure out based on the structure and composition. Okay, so those would be the weak electrolytes, and then the non-electrolytes don't dissociate at all, and that's pretty much everything else. Everything that isn't strong or weak will be a non-electrolyte. So what we're going to do is we're just going to analyze different compounds and then just see. We're going to just ask 2 things. 1, is it soluble? And 2, is it a strong, weak, or non-electrolyte? Sodium chloride. Is it soluble? Well, when we're asking about solubility, first we look at the cation. Group 1 in ammonium. Sodium is a group 1 cation, therefore it's soluble. All sodium salts are soluble. And then the next thing we ask is, what happens when it dissolves? Does it dissociate completely, partially, or not at all? And so since this is a soluble salt, it's a strong electrolyte. Strong electrolytes dissociate completely. So we expect that. I break it up into 2 steps myself. They just have it all in one step. The way I break it up for sodium chloride is like this. Sodium chloride solid, does it dissolve in water? That is, first we ask, is it soluble? And the answer is yes, group 1 salts are soluble, so we form sodium chloride aqueous. And then we ask, well, does it dissociate completely, partially, or not at all? That's electrolyte properties. And then we know that it's a soluble salt, therefore it's strong electrolyte, so it dissociates. It's going to break apart. So the lattice breaks apart into sodium ions, chloride, and chloride ions, aqueous. So it'll look like this. This would be the sodium chloride lattice here. And it's just going to be dissociated or ionized or broken apart by the water molecule. As the ions get broken off here, they get encapsulated by water molecules. It's kind of interesting because, if you look at this drawing, like the green, look at how the water molecules are oriented. We have the white ends of the water molecules oriented towards there. over here, if we look at this gray one, we have the red end oriented. The difference is the charge. This is chloride, and water is what we call polar. There's charge on water. Like the hydrogen ends of water are positive, the oxygen end of water is negative. And so the hydrogen end orients towards the chloride ion because it's negative, so positive and negative interactions. Whereas the opposite happens with sodium ions. The oxygen ends orient towards the sodium. Because the oxygen ends on water are negative, so we help stabilize the ions in solution by creating this, what we call a hydration sphere or solvation sphere. Although it's encapsulated in water, those waters can break apart. There's exchange. So this one can break off and a new one can substitute. So the lattice gets broken apart and we're left with ions, and that's what we have here. Lattice gets broken apart, we're left with ions. Sodium ions, AQ, and chloride ions, AQ. Aqueous just means this. We have the ions dissolved in water here. This is going to conduct electricity because of all the ions in solution. Okay, let's go back and look at this next compound here. What's this called?
Copper chloride.
Well, copper is variable charge, so we need to put a Roman numeral here. I don't like something about this. What don't I like about this? I don't like this space here. Copper 2 should be one word. Copper, no space, and then the Roman numeral here. So the spaces should be deleted here. All right, is it soluble? Is copper 2 chloride soluble? First we look at the cation. Group 1, no. Ammonium, no. If it's not one of those, then we look at the anion. Nitrates, chlorates, and acetates are all soluble. Is it a nitrate, chlorate, or acetate? No. Then we go on to the next one. Chlorides, bromides, and iodides are all soluble except for silver, lead, mercury. Well, this is not silver, lead, or mercury, so this is going to be soluble. And so we have a soluble salt. A soluble salt is a strong, weak, or non-electrolyte. Strong electrolyte. Strong electrolytes completely dissociate. And so we're going to have a lattice of copper 2 chloride. It's going to completely break apart into copper 2 ions, and for every copper 2 we'll form 2 chlorides. Balance it out. So that's what we saw here. Here, this is the copper 2 chloride lattice. Copper 2s are the white ones, and the chlorides are the blue ones. When we dissolve it in water, it's soluble. So one, it's soluble. So if it's soluble, this is what we're going to get. So copper 2 chloride solid is soluble in water, so we're going to get copper 2 chloride aqueous. However, if I have a beaker that's labeled copper 2 chloride aqueous, what's inside of it? So I have a beaker that's labeled copper 2 chloride. Am I going to expect to find any copper 2 chloride molecules? No. Am I going to find any crystals, tiny crystals of copper 2 chloride? No. What am I going to find? Well, this is aqueous copper 2 chloride. What I'm going to find is, well, it's a strong electrolyte, so I'm going to find copper 2 ions. And copper 2 ions in here. For every copper 2 ion, I'm going to get 2 chloride ions. Chloride ions here. Both of these are equal. And so if I have a beaker that's labeled copper 2 chloride, then I'm going to expect to find copper 2 ions. And for every copper 2, I'm going to expect to find 2 chlorides. Note the orientation of the water molecules. The oxygen end of the water molecule is oriented towards the copper tube. The hydrogen end of the water molecule is oriented towards the chloride tube. Here. Okay, it's the same thing. We can dissolve some of it. How much can we dissolve? All of it? Do you think? Yeah. Probably, there's going to be a limit. We can look that up in a table. Like, for example, in Wikipedia, we can find out what that limit is. Some things are infinitely soluble. That is, you can